Small introduction. The second one, actually, everybody knows, or most of the people know, the synergistic effect between the nanomaterials and flame retardant. But today, I would like to focus on this part, functional nanomaterials as a new flame retardant for the polymers. And after that, I would like to share a common conclusion for this aspect. And also, I would like to point out the future of the nano flame retardant. Of course, this is just my own opinion. It can be discussed or it can be complete in the future. So I think the first part is not so necessary to mention a lot because you are sitting here, you know what is fire, what is the flame retardant, and what is the significance to do this research. But nevertheless, you know the polymer have a lot of advantage, and of course, so everything have the two sides, advantage and disadvantage. And disadvantage is the high flammability, so we need to do something for that. So that's why we are here and we do this research. So regarding the flame retardant, you know, basically you have several types: additives type flame retardant or the reactive flame retardant. And also we mentioned the nano flame retardant. So here we just list the three main types. The first one is additive flame retardant. So obviously it means they can directly use to different polymers. And they have the advantage is it's very convenient to use. And also they have the reasonable cost. If you look at the industrial of flame retardancy, most of the products actually belong to this category and they are additive flame retardant. But disadvantage is also very obvious. Normally you need high loading because it's very hard to get a good compatibility with the polymer. So that's why you need high loadings. And due to the high loadings, you will, now on most of the case, it will decrease the other properties or intrinsic properties like mechanical properties or some of them due to the poor stability of the flame retardant. They can reduce the thermal stability of the polymer as well. So that's why people try to find the new flame retardant which can improve the comprehensive properties of polymer. And another type, as I mentioned, is the reactive flame retardant. And this is a really good type of flame retardant. The reason is they can attach with the molecular structures of the polymer, and it can realize the molecular levels dispersion. So that's why they can normally provide the relatively high flame retardant efficiency. But the disadvantage part is it's not very convenient to use because normally if you want to use such type flame retardant, you need to change the synthesize procedure of polymer because they would like to contact with the molecular structures of polymer. So that's why it's not that easy to use it, especially for the industry or manufacture of the polymers. So another type is the focus of the day. It's the nanotechnology or nanomaterials. And these figures, I think, is quite famous. A lot of papers they use these figures. That means the first nanomaterials has been studied. I think it could be the most modernized, and they have a different type of dispersion in the polymers. You could get this such agglomerate dispersion. You could get this intercalation dispersion stage, or you can get the fully exfoliated dispersion, or you can get some of them between. So, but nevertheless, this nanotechnology also have some advantage and disadvantage. So the advantage is normally we only need use very low loadings and to get the satisfied or not really satisfied, but some good flame retardancy. And at the same time, they could improve the mechanical properties or other thermal stability. So this is a good thing. And still, they have the bad things. The bad part is difficult to achieve uniform dispersion. And another most important part is the fail to the vertical burning test. Most of the case, after using the nanomaterials only, you will get really good heat release rate reduction. But it's very hard to pass the vertical burning test, which is very popular in the industry. So that's why we could find in the last 10 years in the Web of Science, if you use the flame retardant plus, just let's say flame retardant or fire retardant by keywords, you will get, I think, totally more than 10,000 publications. And in these publications, if we put another keywords, nanocomposite, you will find it's more than 1,500 publications. It's around 15% of such publications related to the nano flame retardant or nanomaterial-based flame retardant. So that's why actually these directions get more welcomed. Or I think this if you look these values, I think in the future it can be. No, it's another one. Okay, it can be increased because now I would like to point out in this presentation what's the future for such nanomaterials, or where should we go? So regarding the nano flame retardant, normally we need relatively low loading, but you can get a similar result which conventional flame retardant based system. For example, traditional flame retardant, here mainly we focus on the inorganic flame retardant. So normally, if you get a good flame retardancy, probably you will lose the thermal and mechanical properties. But if you use the nano flame retardant to get the same heat release rate reductions, you will get relatively good balance between the flame retardancy and the rest properties. So, but this is some basic information for what is the nano flame retardant. Actually, it's similar, the definition is similar like the nanomaterials. The size, it should be less than 100 nanometer in one dimension. And regarding the different dimensions, we could say the 0 dimensions, 1 dimension, and 2 dimensions. So this is some examples. But in the flame retardant field, most of the people actually, we focus on the 2-dimension structures. It's the nanosheet. For example, nanoclay, monomeronite is one of the most popular studies. So, but the rest, actually, if you look at the literatures, you could also find some people use the 0D dimension structures, also 1D structures. But from the flame retardant effectiveness point of view, it's not that high. So that's why today I will only focus on the 2D, 2-dimension structures and how to improve the fire retardant efficiency for such materials. So here is some examples for as a 2D nanometers. So they have a really good advantage. The first one is the high aspect ratio, and also it's very easy to be modified or to be functionalized. And also, even for such materials, they have some special function. For example, graphite. This material has a good function on the electricity or the thermal conductivity. So if you use such functional nanomaterials, you could transfer this new function to the polymer. So this is the main idea. But actually, in the last 20 years, most of the publications related to the monomeronite. And in the recent years, especially in my groups, in the recent 5 years, we work a lot on the layer double hydroxide and how to functionalize such materials, the main topic of today. So basically, this is the main ideas. Normally, we prepare the 2D nanomaterials and make the functionalization to make the polymer nanocomposite and to study the different properties to try to get a good balance and then use it in the industrial application. This is the main mind of such research in our world. So then first, let's come back a little bit. So we just, because today the training school is not only to show our latest results, so I prefer to explain some basic things to the young researchers. So the first point is the synergistic flame retardant effect between the nanomaterial and the flame retardant in polymer system. So you could find thousands examples. So after using some percentage of nanomaterials, they can improve the fire retardancy in terms of IOI test or U-identifier test or calorimeter test. So I don't want to give more examples because easily from Web of Science you can find thousands of examples. But here I just point out, if you look at this percentage, if you keep the total loading or total additive loading is constant, then if you increase this loading, you will get a good result in some percentage. But if you increase again, for example, in this particular example, if you increase the loading from 1% to 1.5, 2 or 3%, you will find actually the ROI values gets down. So that means they have is optimized the percentage. So you have to be careful to use that material. It's not always increasing. Or this synergistic effect, they need some special ratio between the nanomaterial and the normal flame retardant. So this point is normally, in our opinion, it will be normally between 0.5 to 2%. So normally it's in this range. It can be different according to the different polymer system or different the flame retardant system. But normally this is the range. So if you look at the heat release rate, you will get the similar result. You will find actually after using such nanoclay, they can significantly reduce the heat release rate compared to the controlled samples. And this 20% PP, 20% IFR PP is the control. So you could find even you can reduce the heat release rate. But this is not a new story, because if you read literature, everybody can know this result. And another example is the synergism between the graphene and the intumescent flame retardant. And you could get the similar result at some point, and you will get really good urine antiphotize, and also they can stop the dripping behavior while you burn it. So this is all of this, I would say, is the main conclusion in the last 20 years when the people did this research. Another important finding by using this combination is the anti-dripping behavior. Because people have found if they use only flame retardant, they could generate a charge, but this charge is not that stable, and this charge is easily to move. And how to avoid the dripping behavior, this is another important topic in our flame retardant field. So if you look this pictures is very clear. Actually, from PBS1 to PBS4, all of these samples, they keep the same loading of additives. All of them the same. The only difference is this is without any nanomaterials, and the rest with some nanomaterials. But the total loading is the same. So you could find actually the charge formation is completely different. And if you look the anti-dripping behavior and look this melting flow index, it's very clear. Actually, after using these nanomaterials, for example, this is the PBS4 and this green one, and this the melt flow index of this melting composite is very low. That means it's not easy to generate the dripping and to be removed. So this is the good parameters to stop the dripping behavior, and especially for some polyesters, this is a really important properties. And now I would like to come to the main focus of today. Is the functional nanomaterials in the flame retardant polymer system. So first of all, I would like to share this video with you, and this is also the initial point when we do this research work, because we always think, is it possible to use the nanomaterials only as a flame retardant? Because after using different kinds of flame retardant, they have some disadvantage. So if we can solve this problem, and they can bring a lot of benefits to the either industry or the academic community. But unfortunately, we try to difference nanomaterials. So both of them are commercialized. You know, clay 2030B is the modified monomer and zirconium phosphate. So first, initially, we give a lot of hope to this nanomaterial, because this nanomaterial, the intrinsic structures contain a lot of phosphorus elements. So we hope they can provide a good flame retardancy. But unfortunately, if you look at this video, it's burning like a hell. So there is no any difference compared to the even to the pure polymer. Maybe the only difference is the flaming speed a little bit slow. But nevertheless, once they catch a fire, and they will finish this material after 1 or 2 minutes. So that's why this is really challenging work. And this is actually the main conclusion in the, I would say, in the last 15 or 20 years. People always mention, after using the nanomaterials only, you will get a good reduction of heat release rate. But you cannot pass this vertical burning test, or you cannot change a lot about such test. And occasionally, we got another system, a good system, so which is the layer double hydroxide. So now I would like to show you what's this, why it's interesting. So I got some problem. So could you help me? I tried to use the page down, but that doesn't work. Ah, okay. So then, so page down. Yeah, I think it works.
You want?
No, it's okay. Okay, oh, now it works. It works. No, it's okay. It's okay. Stop here. Yes. So, thank you. So then, let's say this is the question: where should nanoflame retardant go? Because obviously we tried different nanomaterials. It's always so similar phenomenon. So then, it's one nanomaterial that come to our mind. It's named the layer double hydroxide. And this layer double hydroxide, the structure is quite similar with the aluminum hydroxide or the magnesium hydroxide, because only difference is some elements or metal element has been replaced by another one. For example, you can image this is the magnesium hydroxide, but some right point is the aluminum, and the aluminum replaced the magnesium. That's why in order to keep the charge balance, they need the ions in the between. So that's why the layers came out. And normally for these nanomaterials, in the previously they use a lot in the as a catalyst in the organic synthesis, or they use as the biomedical field. But I think the first paper published maybe in the 10 years ago and used as a filler, normal filler for the polymers. At that time, there is no big surprise, because they use it and they find, okay, it's just a kind of fillers, it's nothing special. But we think this area is the harmful area, because we could do a lot of things here. We could make some different molecular design, so that's why in the last several years we did a lot of work on this aspect. First of all, we find a new road to synthesize such new materials, because initially we need to get this layer double hydroxide first, and then we do the functionalization. This is the normal procedure. But during this procedure, we have to avoid the CO2 carbon dioxide influence or the carbonate influence. So it's a little bit difficult to get really good layer structures. So we developed this new method, and we find actually we could use one-step route to synthesize this functional air gauge. So this is a very basic investigation. We found, compared to this pure layer double hydroxide after this modification, actually what we mentioned here is the parent air gauge before modification, and the rest is the modification by the normal procedure. Normal procedure mainly is the regenerated method. So you have to actually calcinate the samples first at high temperature, 400 or 450 degrees, and then you can put it in the water with your modifiers together in order to regenerate this layer again. So this is the, let's say, regenerated air gauge. But if you compare these structures and these structures, you will find by monitoring the aluminum NMR, you will find a new phase is happen, and this new phase is corresponding to the aluminum O4. And this is not typical layer structure. What that means? That means by using the normal procedures, the layer structures cannot keep 100% has been kept in as the layers. Some of them already destroyed. So you cannot guarantee such materials can provide really good performance in your material. But if you compare with this, let's say, one-step route synthesize, there is no any additional phase happen, especially this impurified phase is completely void. So then in the following studies, so most of the case, we mainly following this method to synthesize the different layer double hydrogen. One example here is we use, as we mentioned, actually we could do a lot of things in this area. I mean the layer, the interlayers between this, the intergallery of two layers. So we could introduce different functional modifiers into this area, and in order to get the different function. And this is our motivation actually. First of all, we use this beta cycle reduction, but you know, due to this the nature of this intergallery, you cannot use this molecule directly. You have to modify it in order to make such, let's say, ions exchange. Otherwise, it will be impossible to introduce such molecules into the gallery. So that's why we have to do some synthesize work and in order to insert these molecules. And this is one example, and this is the control. So more work related to the flame retardancy, we did this work. Actually, we designed the different modifiers with different function. And our idea is try to transfer this function from these modifiers to air gauge. And then from air gauge to polymer. Actually, we mentioned this the nano career. And this work has been done by I'm proud of that, my first PhD student, Dr. Aysen Talali now. Because 1 month ago, he got his PhD. So that's why I also congratulate him. But this is really excellent work because we could design the different modifiers with different function. So previously, and people use the modification, maybe it's only for modifying the surface property, and then in order to make a good dispersion, and this is the only purpose. But actually in this work, we are not only care the surface properties, also we try to put more function, and this is the main idea. And if you look this flame retardancy, of course, obviously you can find the difference of the heat release rate, unmodified and modified. I think all of them we keep around 6-8%. But surprising, we could possibly zero. And this is really special result because this is the first time to show using the nanomaterials only, they can pass with zero for such polymer. So before, there is no any such finding. Normally, people have to use the nanomaterials as a synergist, but not only. So as we show in the video previous, so there is no such phenomenon. But here we can find they can completely pass with zero. So another interesting result, later I will show you the video, so because we have the different example. Another important thing is the mechanical properties, because for the epoxy, most important property is, in the mechanical properties, is the impact properties. But previously we find if we use the normal nanomaterials or modified nanomaterials, they always decrease the impact properties. But we are thinking, is it possible to use additional functional modifiers, and his functionality is only to improve the mechanical property or impact property. So that's why we designed another one which is named T, and here we got this system, and they can perfectly improve the mechanical properties. So this is another example. Recently, we got this new result. we try to find the new bio-based sources modifiers and try to use it as a new functional modifiers in these nanomaterials. So we select these structures, and after this chemically modification, so we can successfully get these structures. So if you look at X-ray diffractions easily, you will know, okay, the heat release, the first peak has been moved to the low angles. If you calculate the distance of the layers, it has been improved from 0.76 nanometer to over 3 nanometer. So it's the good opportunity to use this nanomaterials in the polymer, and this is the good advantage. But actually, in our case, we also care what's the function of these modifiers in this polymer composite. So that's why we did this such kind of research. We used the different loading of this organomodified aerodich and also unmodified aerodich as a reference. So look here, maximum we can use this loading as a 6%, and this is extremely low. The good thing is we get the same conclusion as some result reported in the nanomaterial-based polymer system. So we can find actually after using this different loading of nanomaterials, and the heat release rate have a good reduction. And this is not very exciting because even 10 years ago everybody knows this result. But if you compare two results, one is the modified aerodich with 6% and unmodified aerodich 6%, and they have a huge difference. So the heat release rate, the difference is more than half. So this is the good result. So actually, it's according to the previous knowledge. After using the nanomaterials only, you can get a good reduction of the heat release rate. But how good you can get? This is the question. From the top, reduce to here. Okay, this is the reduction. But you could get a further reduction if you get a good modification of functionalization. So this is the one conclusion we can get from this study. And another important thing I think is here, because as we mentioned, after using the nanomaterials, for sure you can get a good reduction of the heat release rate, but it will be really difficult to pass the vertical burning test. So here we select the different examples. For example, the below, we use the conventional halogen-free flame retardant system. So mainly we select this clay 30B as a reference, 6 weight%, 10 weight% zirconium phosphate, and even 30% is a magnesium hydroxide. And with the same polymer, we select epoxy. And here we could find actually all of them is almost the same. After the first or second ignition, all of them cannot stop the fire, and they cannot pass the UR94 with 0. And as a reference, so we need to put unmodified nanomaterials aerodich and normal modified aerodich, also 6%. But actually, if you look such result, it's quite similar. It's not really say there are big difference between these two systems. So if you look, even let's say 30% magnesium hydroxide, they can pass the first ignition, but second ignition, then they cannot stop the fire. They will keep burning. The fire is very little, but nevertheless they cannot stop. So this is the let's say conventional system, and this is the relatively new system. So that's why we are thinking, by using this new nano or let's say functionalized nanomaterials, we hope we can get some difference. So if you look at the last one, and this is actually, we mentioned in the last slide, we can get this video. It's really impressive. So remember, all of them with the same loading and the same material. The only difference is different functionalization. So if you look here, after the first ignition, there is almost no fire catch. so they can easily stop the fire. And following the standard, we need to burn it again for another 10 seconds. And if you remove the burner, it's almost the same. But especially for these 3 samples, and they are exactly the same. The nanomaterial is the same. The polymer is the same. The loading is also the same. The only difference is the functionalization. So that's why we point out for such materials, the functionalization is really important. And this could be one of the let's say, the future directions for such studies. So then we try to understand the mechanism. So obviously, we only use the nanomaterials, so it should be relatively easy to understand the mechanism. But actually, it's not. So we do a lot of effort to clarify the mechanisms in the gas phase and in the condensed phase, use the different technology. But nevertheless, we find some interesting results. If we do this TGF-DIR, we analyze all these peaks, and we got this information. It looks very interesting. We select several special peaks, like hydrocarbons, like esters, like aromatics peaks, and all of them, they provide the same conclusion to us. That means after using these nanomaterials, the intensity of these peaks is always decreased compared to the reference sample, compared to the polymer only. So that's why we could get this conclusion: the release amount of flammable hydrocarbons, esters, and also these aromatic compounds are reduced. Of course, we cannot say we analyze all of these flammable products, but at least these 3 main compounds is the main compounds in the flammable structures. So we do believe in the gas phase, the flammable product is less than the controlled samples, and this is in the gas phase. And if we look the condensed phase, we also find it quite different. So this is use the different loading of the modified nanomaterials. If you look the pure epoxy without any nanofillers, this is the surface of the char. And after using the different loading of the clay, and this performance has been improved 1%, 2%, 4%, and 6%. So from these microstructures, easily we can find actually up to 6% we will get very good the char residues, especially with more impact or more continuous without open holes, and all of them can influence the transfer of the heat or gas or the oxygen. So this could be a reason to reach the good flame retardancy. And also we try to monitor the temperature of this char during the burning. We try to monitor 2 parts. One is the surface, the temperature of the surface, and the temperature is inside, under the char. So we got the different result. It's quite interesting. So if you look, the black one is the outer surface. So outer surface actually it means the surface of the char is always the same. So it's easy to understand because above this char is the corn heater. So almost the temperature is very constant. It's around 700 degrees. But if you compare to the rest samples, it's quite different. If we use the 1% to 6%, and this temperature is quite different. Especially if we use this 6% modified air gauge, actually under the char, the temperature is only around 400 degrees. There are around 200 or 250 difference compared to the reference samples. So you can imagine such 200 degrees difference can generate a big difference in the flame retardancy. So I didn't put another reference, so actually we did, but I have no time to put here. It means another reference is the unmodified air gauge 6%. It's a really good reference. And actually that the result is quite similar with this green one. If we use 6% unmodified nanomaterials, it will reach here. So still we have more than 200 degree difference. So that's why we think in gas phase or condensed phase, and they can generate such big difference. So then, according to this research, we could get some very general conclusions, because I don't really want to make this presentation too long and so boring for you. So I just give you this very general conclusions. The first one is very clear. Nanomaterials are excellent flame retardant synergists for conventional flame retardants. And second one is the nanomaterials has the possibility to become an independent, eco-friendly flame retardant for polymers. But unfortunately, so far, for this study, it's very limited. We are still on the journey to do this work. Regarding the flame retardant mechanism for these nanomaterials, actually the first two is already confirmed or proved by many times, and they can provide a good barrier effect and to slow down the mass or the heat transfer. And the second one is they can promote the char information. So both of them actually is already proved. But in our new findings, we found actually probably they have another new mechanism. So now we are working on that. Otherwise, it will not get such result what we achieved recently. So we try to understand what is really happened behind of this behavior. And this work we are working on. And the challenging for this nano flame retardant still have two. One is still the dispersion, and dispersion things is always a challenging problem for these systems. Of course, it's strongly depending on the polymer system. High viscosity, low viscosity, solution blending, melting blending, they have the different factors to influence such properties. And another challenging, actually, recently, more and more researchers aware, this is the really important point, is the interaction between the nanomaterial and polymer matrix. And this is not only the dispersion things. This could improve other properties, not only dispersion. So I would say, for nanoflame retardant, dispersion is very important, but it's not the only factor. So we have to consider more. So that's why I just put out some several slides to say what is the future for the nanoflame retardant. So here there are some nanomaterials. All of them have been used in different polymer systems in order to improve the flame retardancy, either as a synergist or as a single flame retardant. But the future of such nanomaterials should be functionalization. I think functionalization is really important for improving the efficiency of flame retardant for this material. But the key point is, what is the mean of this functionalization? Because different people have different understanding. And here I only point out several ones, what I thought is really important for the future. And the first one we mentioned is the employment of the functional modifier. Because previously, when people talk about functionalization of nanomaterials, it's mainly focused on the modification of the surface. Okay, in order to get good dispersion, in order to make a good compatibilism with the polymer, blah blah things. But we should think about the functional modifiers, and these functional modifiers maybe can improve other properties. Flame retardancy, of course, if you use the flame retardant modifiers, it could be better than the flammable modifiers. Remember that most of the modifiers in the market, they are flammable. So you could use it to modify your nanomaterials, but at the same time, actually, you introduce a new flammable product in your material. So this could be a first thing we should think about. And the second one is I mentioned here, is the hybridization of intrinsic structure. And what does this mean? Because normally, we know the synergistic effect between the nanomaterials and the flame retardant, between different nanomaterials. Nanomaterial A plus nanomaterial B, they could generate a good synergistic effect rather than use only one. But it is possible to do this hybridization of intrinsic structure. For example, actually, the layered double hydroxide is one example. And if you compare their parents, one is the magnesium hydroxide, one is the aluminum hydroxide. But if you use these nano materials only, you will never get good result. But if you put them together in the intrinsic structures, it's not only a physical blending, it's the hybridization in the element scale or molecular scale, then you could get a really good result. So currently in my group, we have several new examples. I have no time to show here, but in different polymer systems, and we get really good result. After this hybridization in the molecular levels, we will get really good improvement. It's a kind of synergism, but at the molecular level. And the last one we claim is I would say, is the nano architecture. And this is the more high levels thinking about this research. Because now we could easily get nanomaterials, functionalized nanomaterial. Easily we can get them, and easily we can make processing and to make the polymer composite. But if we can realize the nano-architecture, we could put several functionalized nanomaterials together, and they also have the different function, and they could provide even better results. So just following this idea, just very recently, we got this one new result, and this result actually you could find this new nano flame retardant system not only provide good flame retardancy, also they can provide really good mechanical properties. At the same time, they can provide really good anti-UV properties. So the idea is we try to put more multifunctional modifiers for these nanomaterials. They could have the different functions. So I think this is one of the, let's say, the futures, or at least one direction for such research. So finally, I have to thank my groups in Madrid, and especially for several previous members who did a really good contribution for this result. But today, Aysen Kalali is here, so thank you very much. And the rest, two postdocs is already gone, but they did excellent work in the last 2 years. And also I have to thank the financial support from different organizations in the last 2 years. And also I'm very happy to be here and to show this idea, or to show this, let's say, some new result to you. I would like to make any discussion with all of you. Thank you.